Welcome to the course Digital Control in Switch Mode Power Converters and FPGA-based Prototyping. I am Teja Golla. I am a third-year research scholar working under Dr. Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. I hope I'm audible. So I guess you have already gone through week 1 lectures. So I'm planning to do in this session. First, I'll be discussing about the concepts that have already been taught by sir in the week 1. So I'll give a brief revision of all the concepts. Since it is a week 1, which is very introductory, we don't have many problems to solve, but we'll be discussing about few problems towards the end of the session. So in the beginning session, I'll be discussing about the concepts, main concepts, crucial concepts that you will be needing for the upcoming weeks. So I'll be briefly discussing about them. If you have any difficulties, please stop me and ask me at the moment. And if you feel I'm going too fast, please let me know. And this will be more like an interactive session, not like a lecture. So let's interact with each other, and I hope I will be able to help you in understanding the concepts. So if you ask me more doubts, then I will also try to help you during these sessions. Hello, someone is saying that my audio is lagging. Can anyone confirm if it is okay for others? Hello.
Sometimes your voice is breaking, sir. Sometimes.
Okay. I hope it is better now.
Now it's clear, sir. Now it's clear.
Okay. So let's get started. So first I'll be giving a brief presentation of the concepts that are covered in week 1. So when I reach that particular specific topic where you are having doubts, please stop me and we can discuss further. And towards the end, we'll solve very basic problems. But from the next week, we'll solve the problems rigorously, because as week 1 is only introductory session. I hope my screen is visible. Can anyone confirm?
Sure. Visible, sir.
Okay. So welcome to the course Digital Control in Switch Mode Power Converters and FPGA-based Prototyping. Myself, Teja Golla, a third-year research scholar working under Dr. Santanu Kapat, also at Embedded Power Management Lab, IIT Kharagpur. So this practice session is regarding the week 1, which is Introduction to Digital Control in Switch Mode Power Converters. So brief introduction about myself. So I have completed my BTech here at IIT Kharagpur under Santanu Kapat, and I have joined PhD here at IIT Kharagpur, and now I'm in my third year, and I'll be the TA for this practice sessions for this course. So let's go to the week 1, Introduction to Digital Control in Switch Mode Power Converters. So in this session, we'll be discussing about these aspects. So the overview of this session is as follows. First, I'll be discussing about the introduction to digital control. Why do we need digital control? What are the advantages of digital control? And are there any challenges in the digital control? If yes, what are those challenges? And also, I'll be giving an example of commercial digital control IC, which I think Sar has already discussed. I will be discussing further more detail. And then I will be discussing about FPGA versus ASIC. What are the advantages of FPGA and what are the advantages of ASIC? Why are we going to FPGA-based prototyping and experimental results in this course? Why we are not choosing ASIC? Is FPGA better, or are there any trade-offs between them? We'll be discussing about them. And then I'll be discussing about the variable control techniques that SAR has already revised in this week 1, and these control techniques are very crucial during our journey in this course, and SAR will be implementing multiple control techniques both in simulation as well as hardware. So it is very important that you understand all the control techniques as we proceed. And first we'll be discussing the analog implementation of the control techniques, and just a minute. I hope my pointer is visible. So, and then we'll be discussing about the digitization of control loops, how we are going to digitize the loops, what will be the changes when we move from analog to digital, what are the challenges, what are the aspects that we have to consider, all these things. And then I'll be discussing about power stage design of a buck converter and boost converter, and towards the end we'll solve few problems. So coming to the digital control, what are the benefits and challenges? So in the case of digital control, we have so many advantages. A few of them have already been discussed by sir, which is the flexibility and reconfigurability. So in the digital, it is nothing but a code that has been dumped into FPGA or made into ASIC. So there is a lot of flexibility for us. We can change the gains, and we can implement complex algorithms by means of using the code, and then we can dump it into the FPGA. Whereas in the case of analog control, you are using the analog devices components and you are mounting on the board, and there will not be much flexibility as much as the flexibility that will be getting in the digital control, and also digital communication. So this part I'll be discussing briefly when I discuss about the product IC product. So if there are say multiple ICs there, and there has to be some communication among the ICs. If you use another digital IC, then we can use either PM bus communication or I2C communication. So this main IC will be communicating with the small ICs, and I'll be discussing about it in the upcoming slides. And also hardware software integration. So whatever code that we'll be writing, it is software, and we'll be dumping the code into hardware. So there will be this integration between hardware and software. Also, if you use microcontroller, there also will be using some softwares which will communicate with the hardware by means of that software. So this hardware software integration will be there. And also when we make an ASIC, we'll be designing it for higher efficiency as well as power density. So whatever IC that we'll be making, it will be highly power efficient, and also it will be having high density. And also we can make a digital PMIC out of this. So as we go into the further weeks at around from week 6 to week 12, we'll be discussing about Verilog. So that Verilog code we can eventually design an IC out of it. And also the prototyping will be rapid in the case of digital control. So if there are so many advantages, you might ask, are there any disadvantages? Yes, there will be few challenges, like the cost. We'll be using ADC DAC. So because of that ADC DAC, the cost of the complete implementation will change, and also there will be multiple levels of digitization. So we'll be discussing again this in the upcoming slides, and it will increase the complexity, and also it will create other stability issues which we'll be discussing. And there will be multiple architectures we have to be considered when we go into the digital control. And also the power consumption. As we are using ADC DAC, the power consumption will increase, and again there will be a trade-off. If you are using high sampling frequency for ADC, then the power will be less. But if you sample it at a smaller, lesser frequency, then the time delay will be more, which will cause stability issue. So there will be always this cost versus power trade-off when it comes to ADC, DAC, all these things. And you have to consider the time delay when you are modeling, and you have to analyze accordingly. There will be some stability issues which you have to consider, and all this modeling and analysis will be discussed in the upcoming weeks. And also the design methodology for the controller will change slightly from the analog control, and we will be discussing that rigorously in the upcoming weeks. So coming to the experimental prototype. So this is the experimental prototype that we'll be using in this course, and Sar has already shown this in the his video lectures. And whatever hardware results that we'll be showing in the upcoming weeks are performed on this. So let me use a pen. So as you can see, this is the power stage. So this entire thing is the power stage. Okay. So this entire thing is the power stage. And this part is the signal conditioning board. I hope I'm audible and you can see me writing on the screen. Can anyone confirm?
Yes, sir.
Yes. Okay. And if you have any doubts, don't hesitate. Please kindly ask. You can stop me at any time.
Okay, sir. Okay.
So this is the power stage, and it has both buck converter as well as boost converter. But currently we are operating in the buck converter. As you can see here in this region, there is a switch. So the left side means buck and the right side means boost. So the layout has been done in such a way that when you push this button to the left, it will operate in buck condition. And if you push this onto the right side, it will operate in the boost condition. So when you are operating in the buck condition, you can see this port, right? This is the V input and this is the ground. So here we will be giving the input voltage with respect to this ground. And here are the two switches, as you can see. low side and high side switches. And this point is the switch node. This is the switch node. I am writing switching point. And here you can see there is a wire. This wire is basically for current probing. So we'll connect the current probe so that we can view the current waveform in the oscilloscope. So this provision has been made to view the current. And then next to this, as you can see, this is the inductor. This is the inductor. And then it is connected to the output stage. And these are the capacitors of the output stage. So these are the output capacitors, and these are the input capacitors. And these are the load, and we'll be using these resistors to give load transient. And if you see this part, okay, let me change the color. So if you see this part, I think this is not visible. If you see this part, this is for the sensing, mainly for IL, comma V0 sensing. So this is needed for our controller when we are using voltage mode control, current mode control. Depending upon that, we'll be using this sensed inductor current and output voltage. And this part, if you see on the right hand side, this is the auxiliary supply. So whatever auxiliary voltages like +3 -volt, +5 -volt, whatever that will be needed for this current sensing will be generated by the circuitry. And if you see over here, you can see 2 pins here exactly. So this is supply that we'll be giving, which is +12 volts and ground. So this is the supply that we'll be giving to this board, and here V input as well as here V ground. So this is the V input and this is the ground terminal. This is the supply input supply that we'll be giving to the buck converter. And for the auxiliary supply, to generate the auxiliary supply, we'll give +12 volts ground, which will generate +5 volts, -5 volts, whatever that is needed for this sensing part. And this circuitry is for IL as well as V0 sensing. Regarding the circuit that we have used here, will be coming in the upcoming weeks when we discuss about the sensing. So now this IL and V0 sensing are generated. And this is another signal conditioning board where we will have ADC, DAC, comparator, and below this, you can see a top board. Below this board, there is this FPGA. I'll be showing that board in the upcoming slides. So if you see this, this is the connector connecting the main board to the signal conditioning board. So whatever signals that are coming in this region will be going into this region, and they are given to different terminals. So say V0 sensing is there. V0 will be coming to this IC, and this IC is ADC. So input will the V0 will be coming entering the ADC, and these are the output of the ADC. So we are using 10-bit ADC, and all these details again we'll be discussing very rigorously when that topic comes. I'm just giving a brief understanding about what we are doing here. So we have used a 10-bit ADC. So the output will be like 10-bit in digital format. And now these digital signals will go to the FPGA, which is sitting right below this top board, which you are seeing. And then that digital signal will be coming back, because whatever we perform in actual world, all are analog signals. Only the controller, the FPGA, will perform all the actions in the digital signals. So whatever signal that we have to generate back, it should be analog. So that's why for that purpose, we have another DAC. This DAC will be used only in current mode control, not voltage mode control. So from the below FPGA, we'll get the signals. So the input to the DAC, this is again a 12-bit DAC. Why we have chosen 12-bit DAC and 10-bit ADC? Why not 1010? This will be discussed in the again future. There is a reason why these are more number of bits than this. It is related to the stability criteria. We'll be discussing the stability issues, everything in the future. Now I'll be giving just a brief introduction about this. So the output of this DAC will be again analog signal, which will be going back to this connector, and from this connector it will go to the there is a gate driver here, so and it will generate the, this is the gate driver, and it will generate the switch. So from the power stage we are sensing the inductor current V0 in this region, and these signals are coming into the signal conditioning board. Here we are converting the analog signals to digital. We are sending it to the FPGA where our code is dumped. So whatever logics that we are writing in Verilog, that will be dumped, eventually dumped into the FPGA. There all the process happens, and that signal will again come to this PWM signal. In the end, whatever control technique we will be using, finally it has to be reflected to PWM signal, right? So whatever logic that we'll be using here, finally it will give the PWM signal, which will be coming back here, and accordingly the buck converter will work. And here you can see there are these three are switches. So these switches can be used for giving transient. So we can write a code in such a way. So when switch is off, it is operating at light load condition. When switch is on, it is operating at high load condition. And maybe this switch we can use for reference transient. So when switch is off, it is having low output voltage. When switch is high, it will be having high output voltage. All these things we'll be again discussing in the future. I'm just giving an overview. So this is the buck converter that circuit, digital circuit, equivalent circuit of the same. And so this is all about the experiment setup that we are going to use. And when the the same concept comes, I'll be discussing again in detail. If you have any doubts, you can ask me at this moment.
Sir?
Is auxiliary supply for setting reference output voltage? No, auxiliary supply is for the ICs. Here, as you can see, we are using different ICs in this region as well as different ICs in this region. Some might need +5, -5, some might need +12. So we will not give all the voltages that we need. We use this circuitry. So there is something called LDO. Using this LDO, we'll generate the necessary voltage from this 12 volts. Say we need +5, -5. We cannot give all voltages from the external supply. It is not possible and it is not recommended. So we'll give one universal supply, and from this we'll generate the necessary voltages, and it will be sitting here. And as you have asked, we are doing the digital control, and you can see this V reference is in digital domain. So it is mentioned in the code itself. So whatever V reference that we want, it will be mentioned in the code. So this is in digital domain, not analog domain. So this V reference will be coming from the code. I hope I have answered your question. Why there are 4 capacitors at the output and 4 at the input? So it again depends. Like this may be of 10 microfarad, this may be of 100 microfarad. By considering the ripple requirement, what is the value of capacitance that we need? Say we need 100 microfarad. We can either use a single 100 microfarad. I can use 10 parallel 10 microfarad capacitor. So actually this is a good question. Thanks for pointing out. So say we are using a single capacitor of 100 microfarad, or we can use 10 microfarad, 10 such capacitors connected in parallel. So what are the advantages and disadvantages? Theoretically speaking, both are same. If you simulate it, both will give the same result. But in the case of hardware, another thing, one crucial thing that we have to consider is the ESR. So every capacitor will have ESR, right? Say this has some ESR, this will have some ESR, this will have some ESR. Say this ESR is R ESR. And we have connected 10 ESRs in parallel. Each capacitor is having 10 RESR, right? So now the effective ESR will be RESR by 10. So we connect multiple capacitors in parallel so that the effective ESR will be 10. Now you may ask me, instead of connecting 10 microfarad 10 capacitors, I'll connect 1 microfarad 100 capacitors. But again, it comes to the space requirement, right? We cannot like fully increase the capacitance. So there will be this space constraint as well as this ESR constraint. So we generally consider a few around 10 capacitors or so. So I think according to the calculations they have used, if you can see there is one big capacitor and one small capacitor. I think those are of different values. So big capacitor is of big value and small capacitor is of small value. So the effective ESR will be in parallel, which will reduce the total ESR, and the capacitance will be summation. So for that reason, we'll use multiple capacitors. Okay, I hope you have understood this slide. Can I move to the next slide?
Sir, how the RS flip-flop is used? Sir, I am unable to hear your voice. Sir, your voice is not audible.
Sir, your voice is breaking occasionally, sir. Sir, we couldn't hear you.
Hello, am I audible now?
Yes, sir, you are audible now.
Sir, now it's not audible.
Hello, now?
It's audible now.
Okay.
And it
So
is breaking, sir.
still breaking.
No. After you
Occasionally.
start speaking, after some. Yeah, yes, sir.
Okay. You may ask me, like you may tell me when my voice is breaking. I'll repeat what I told. Okay.
You are in the process of explaining, suddenly it breaks, sir. That's why we
Acha,
couldn't
okay.
interrupt at that time.
Okay. I think there is some network connectivity issue. Hello. Hello. Hello.
Now it is audible.
Okay. So someone is asking what is the purpose of DAC? So in the case of current mode control, we'll be using DAC. Again, I'll be discussing about current mode control briefly in the upcoming slides. So I'll be discussing there. Currently, I will not explain because here you might not understand the use of it, but I'll be discussing in the upcoming slides. So moving on to the next slide. So this is one commercial digital control IC that Sar has discussed in one of the lectures. So this is one of monolithic power systems IC, a controller IC.
Sir, could you please repeat how the noise is eliminated in the RS flip-flop, please?
Okay, again, I have put this SR flip-flop in the upcoming slides. I can briefly explain it with the waveforms.
Okay, sir.
Okay. So commercial digital control IC. So this is one of the IC of monolithic power systems, and this is another power stage, buck power stage. So what they're saying is we can connect 10 such ICs to this particular IC. If you can see here, there is CS1 to CS10, again PWM1 to PWM10. So these are all current sensing, which is coming from this IC, and this is taking the information from this IC and then giving the PWM signals to all these ICs. So we can connect up to 10 such phases, and it has this PM bus I2C component communication between them. So this controller can communicate accordingly, and it will take data from this, and then accordingly it will send the PWM. This is one digital control IC, and its switching frequency can vary from 200 kilohertz to 5 megahertz. Also, it has this nonlinear digital control for faster transient response. And if you know something about multi-phase buck converter, it has some issue called current balancing issue. for that, people use different algorithms to achieve this current balancing, and this digital controller has inbuilt auto phase shading as well as current balance and automatic loop compensation also available in this digital control. This is one such example of digital control in the commercial IC aspects, but there are several such ICs that are already available, and Sir has discussed in the lectures. So someone is asking where does the recording will be uploaded. So I am recording this session, and this will be uploaded. Just a minute. So this will be uploaded into YouTube, and that YouTube link will be given to you by the NPTEL people. And also all the lecture notes, everything will be shared with you by NPTEL people. I will upload it to my drive, and I will share the link with NPTEL people, and they will circulate the link with you. So coming to FPGA versus ASIC. So now we have discussed the importance of digital control. Digital control can be implemented in any FPGA, also ASIC. So what is the main difference? Why are we going for FPGA? To understand this, we have to understand the implementation of ASIC, how we are going to implement something in ASIC, and how we are going to implement something in FPGA. Let us consider two input AND gate. How was the DC bus created from the output of the converter? Ceramic capacitor are used for filtering. Yes, the output capacitor is to take the ripple. So the inductor current will be having the ripple. So output capacitor is connected considering the ripple requirements and also the transient. So depending upon the output capacitance is selected, and we use ceramic capacitors, and we connect multiple of those capacitors in parallel to reduce the ES. So we'll be discussing about FPGA versus ASIC implementation, mainly the CMOS implementation. To start with, this is the first we'll discuss about the CMOS implementation in ASIC. So here we have seen this is a 2-input NAND gate. So how this is an NAND gate? So here we have this is a PMOS. So these two are PMOS, and these two are NMOS. So let us draw the truth table A, B, X. So if A and B both are 0, what is X? If 0, 1, what is X? 1, 0, what is X? 1, 1, what is X? So if A and B both are 0, this is 0 and B is also 0. So this will be open. These two NMOS will be open, and both PMOS will be on. So VDD will be passed through X. So X will be 1. And in such way, if again A is 0, B is 1. So A is 0 means this is off, this is on, and A is 0. So this is on, this is off. So again VDD will be connected by means of A. So again this will be 1. Let me change the color. Now we are considering A to be 1. So A is 1 means this will be off, and B is 0 means this will be on, and A is 1. So this will be on and this will be off. Again by means of this connection, X will be 1. Again pointer, let me change the color. Now A and B both are 1. So this is off, this is also off, this is on, this is on. So it is connected to ground. So X will be 0. And this is implementation of what? When AB is 1 and 1, X is 0. So X is AB bar. So this is an implementation of NAND gate. But if you want AND gate, what we can do? We can do NOT of this. And how we can implement a NOT? We can use a CMOS inverter. So this is a CMOS inverter. So the front stage is NAND and the next stage is NOT. So Y is nothing but, so this stage until this point. Am I audible? And this is not. So the overall implementation is AND gate. Yes, okay, thank you. So how many gates do we need for the implementation of a 2-input AND gate? How many gates we need? So this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. So for CMOS implementation, the number of transistors that we need is 6. So keeping this in mind, let's go to the lookup table based implementation of the same gate. So when we are going to the lookup table, so AB, there are 2 inputs. So there are 4 such possibilities: 0, 1, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. And depending upon the output that we need, they'll vary. So if we want an AND gate, so why this will be 0, this will be 0, this will be 0, this will be 1. So this is the implementation of an AND gate. Sir, why cannot we connect NMOS to VDD and PMOS to ground? Because of their requirements. See, NMOS need the voltage that we'll be giving for NMOS is VGS, right? VGS should be greater than VTH. And this source is connected to ground, and VTH is say around 0.7 volts to 1 volt. Whereas in the case of NMOS, we need to give VSG. So this will be connected to positive side, so VDD, and VSG should be greater than VTH. So that's why we connect PMOS to high voltage and NMOS to low voltage. So coming to the lookup table based the 2 input logic. So we have such, depending upon the requirement, we'll have this Y0, Y1, Y2, Y3 values already decided, and accordingly we'll implement this lookup table based implementation. So how many possible functions are can be, like, how many functions can be possible for n inputs? Say here we have 2 inputs. Now let me change the color again. And also I am not using the pro version of Zoom. So each session will be 40 minutes. So 3 minutes are remaining in this session. After this 3 minutes, the meeting will be automatically closed. I'll open the another meeting in the same link. We'll continue our discussion. I hope everything is clear. Within 3 minutes, this meeting will be ended, because this is not a pro version, and the limit is 40 minutes. After 40 minutes, the meeting will be closed. In the same meeting, I'll join again. You also please join again, and we'll continue our discussion. Okay. So for 2 inputs, we have 2 possibilities of Y0, 0 and 1. Here also 0 and 1. Here also 0 and 1. Here also 0 and 1. So here we have 2 possibilities. Here we have 2 possibilities. Here we have 2 possibilities. Here also we have 2 possibilities. So overall permutations combinations will be 2 to the power 4. For how many input? 2 input. But say there are n input. Say there are n inputs. Say A1, A2, up to so on, AN, and Y is there. So this can be 0, 0 up to so on 0, 0, 0, 0, 0 up to so on 1. And this will continue until 1, 1 up to so on 1. So how many such possibilities will be there? Hello.
Yes, you are audible now.
Okay, okay. So what I'm discussing, so there are 2 to the power n such possibilities, and each possibility has y.
Sir, please repeat from that point. Why it's not audible? Your audio is not audible, and
Okay.
we are unable to see what you written.
Okay, okay, sorry. Okay, let me explain. So what I'm discussing is the lookup table based implementation. If there are 2 inputs, how many such functions are possible? So if there are 2 inputs.
Your voice.
Hello.
Yes, sir, it's audible now.
Okay, I guess I am having some internet connectivity issues. If there are 2 inputs, then output can be either 0, 0, 0 or 0, 0, 0, 1. So each Y0 will have 2 possibilities. So here 2 possibilities, here 2 possibilities, here 2 possibilities. So for 2 input, the number of possible functions is 2 to the power 4. And if there are n inputs, instead of AB, I have A1, A2, A3 up to so on n, and Y is the output. How many here? There are 4 permutations of combinations of inputs, right? Here, how many permutations can be possible for input? This can be 0, 0, 0, 0, 0, 0, 1 up to so on 1, 1, 1. So it will be 2 to the power n possibilities for the input side. Now output, for each possibility of input, output can be 2. Either it can be 0 or it can be 1. Similarly here, sorry. Similarly, in the second case, it will be 0 or 1, and up to it will be 0 or 1. So for each value of input, there are two possibilities of output. So total, how many permutations are possible? Sorry, 2. So this 2 into 2 into 2 into 2 into 2 up to 72, and how many 2s are available? 2 to the power n. So I hope everyone has joined. So let me continue. Is my screen visible?
Yes, sir, it's visible.
Okay, thank you. So each case output will have two possibilities, and how many such 2s are there? 2 to the power n. So it will be 2 into 2 into 2 into 2. 2 to the power n terms are there. So it will be 2 to the power 2 to the power n. Such possible functions are available for an input lookup table. So coming to the next implementation. So now, as we have discussed this lookup table LUT, this has y0, y1, y2, and y3. Now coming to this part. So say y0 is 0, y1 is 0, y2 is 0, and y1 is 1. So output y we need what? A into b. So we are implementing this by means of mux. So this is one 2 cross 1 mux, and this is another 2 cross 1 mux, and this is another 2 cross 1 mux. So say if b is 0, a is 0, which value will be taken at y? So b is 0 means here, and this value will be taken here, and here this value will be taken here, and since a is 0, this will be taken. And also for other cases, if b is 1, a is 1, 0, b is 0, a is 1, b is 1, a is 1. And when b is 1, a is 1, let me draw. So when b is 1, this value will be taken here, and here also b is 1, so this value will be taken here, and since a is 1, this will go here. So this is an implementation of y equal to ab by means of a lookup table. So the outputs are here, and we are using muxes to implement this. So now we have to discuss how many CMOS are needed to implement this y0, y1, y2, y3, also this mux. So this sir has explained. I will explain just very quickly.
Sir, in the before circuit, like if I want to implement a plus b, then may I need to store the a plus b result in the y0 to y3 then?
Yes. So in the case of a plus b, the values that will be stored in y0, y1, y2 are 0, 1, 1, and 1. And again, using the same implementation, accordingly.
Sir, may I need to follow some any like 0 1 1 or 1 1 0? Can I use that, or is there any specific order?
Yeah, whatever values you take, it depends upon the B and A selection. See, if B is 0, see, you have to see what value is being taken to the output. See, y0 will be taken. Sorry. So I'm writing here. So y is equal to y0 if a is equals to 0, comma b equals to 0, and y is equals to y1 if b is a equal to 0 and b equal to 1, and y is equals to y2 if a equal to 1, comma b equal to 0, and y is equals to y3 if a is equal to 1, comma b equal to 1. So according to this, because whatever mux we have used, whatever the way we have selected b and a signals, we are getting the output in the similar way. So if you want to select this y0, y1, y2, y3, you have to select it accordingly. You have to see when a equal to 0, b equal to 0, y is equals to y0. So for your summation, y0 is 0, and when a equals to 0, b equal to 1, your y1 is 1. And for your a equal to 1, b equal to 0, your y2 is 1. And for your a equal to 1, b equal to 1, your y is y3. So you have to map this y0, y1, y2, y3 with the circuit that you have chosen. Accordingly, you should take. So it can see, so this will always be 0, this will always be 1, this will always be 1, this will always be 1. That won't change. You cannot take 1110 So whatever circuit that you have selected, whatever the selection signals A and B are available, with respect to that, you will get y0, y1, y2, y3 values. So in this case, we have selected y equal to AB. So the values are 0, 0 and 0, 1. Now we have to implement this circuit using CMOS logic. So in the case of CMOS, this Y0 has to store data, right? So for that we use SRAM cell. So how this SRAM cell works? So here one switch S is there. So when this S is on, the input will come here and it will store. This is a bistable latch. So whatever value it is there, say here X value is there, here X bar will be there and X bar will be there, X will come in. So this bistable latch will hold the data, and whenever this S bar is on, the input will go to output. So we use this in general SRAM cell to store this data of Y0 or Y1 or Y2 or Y3. And how many transistors we need? Here one transistor, and here how many? 2. This is an inverter, so we need 2. Here also inverter, so we need 2. And this we need 1. So in total, we need how many transistors? 2 plus 2, 4, 5 plus 1, 6. So 6 transistors are needed for a single Y0, but we have 4 of them. So it will be 6 into 4. That is equals to 24 cells. Transistors are needed for storing the data of this Y0, Y1, Y2, and Y3. So we have how many cells? 24 cells. And this is about the Y0, Y1, Y2, Y3. And then we have used mux, right? So this is the mux. So depending upon the select line.
Sir, please once, sir, suppose I have turned on S and then S bar is definitely will be off position.
Yes, yes.
When S bar is on, will the data got erased within the loop where the
no, because see, if some data is coming here, that data will be not here, and again that data will be the same here.
Irrespective of S and S bar.
So the data will be staying within this loop, so the data will not be erased. The data will be stored here.
Sir, if I want to, I want another data to enter this bistable multivibrator, then what should I do then?
So that your input will be varied. So
Okay,
whatever input you want, that input you will be giving to this SRAM cell.
Okay.
And accordingly it will vary. But we have 4 such data, right? We cannot give 4 data to the same SRAM cell. We have to use 4 different SRAM cells.
Yes, but if I just gave input 1, then that will be 1 and 0 and 1 will be available. If I want to give the input 0, then what the thing will be done?
Sorry, can you please repeat your question?
If I want first point,
Hello. Hello. Sorry, you are not audible.
I want to store 1.
Okay.
Voice is not audible.
Yeah.
Suppose if I want to give input 1, then it will be enter the bistable multivibrator.
Yes.
Then if I want to give 0, then how the transition will take place?
Same, like whatever may be the input, it will be stored in this bistable latch, which will be eventually going to the output. Like it can be anything. Like the working is in such a way, when S is on, S bar is off. So when S is on, the input will come here, and this will be on. And when this is off, this is on, whatever value that you are storing here will go to the output. So at a time only one will be working. Understood?
No, sir, no, I didn't get the point.
See,
I want to state transition from 1 to 0 and 0 to 1 when the input is changed.
No, I'm saying whatever may be the input, if S is on, input will be coming to this circuit, right?
Yes, sir.
And when this switch is off, that will go into the output.
Okay.
So
if
both
the
will
S
not be
bar
on
is
at a
on,
time.
then
Both will not be on at a time.
Okay. If this is the case, then the 1 will be go to the output. Will
Yes.
there be anything in the bistable multivibrator or it got erased?
No, it will be there. It will be there until you erase. It will be still be there because we are not erasing, right? We want this to hold the value. We are not erasing it. We want this to hold the value, and whenever we want to use it, we'll short this S bar, so it will be available at the output. We want to store the data. Whenever we want to erase, then we can erase.
Sir, but the thing here is, yes, sir. Yes, sir.
Yes.
But to store 0, I have to give the input 1, right?
Actually, the output will be inverted. So output will be input bar because of this
Sorry?
inverter. Output will be input bar because of this inverter. Understood? Like output is input bar because of this inverter. When S is shorted, here you will get input, and when S bar is shorted, output is input bar.
Yes, sir. If the thing I am saying is, if I want to store 0, I have to give 1 as input, right?
No, we will give 0 as input, but output you will get 1. Again, you have to use inverter for the further computation. You
No,
don't
sir,
have to
it's
change
not
input.
clear.
See. I'm saying, say input you have given 0.
Yes.
Output you will get 1.
Yes.
Then you again have to use inverter to get the input.
Okay.
Understood?
Okay, sir. Okay. But if that is the case, I need like 7
Plus 2, actually 2. This inverter is also added. So this will have another 2.
Sir, then the number of transistors for each
Will
SRAM cell
increase.
will be 8, right?
Each will increase. Yes.
But if that is the case, is that 6 into 4 equal to 24 is wrong then?
Yes. It will be like, I think it will be plus 2. And this will be 32. This will be 8. You are right.
Okay, sir. Thank you.
Yes. Now coming to the MUX implementation. So for MUX, there is this select line. Depending upon the select line, either A will be going or B will be going. Say if the select line is 0, say S is 0, then this will be 0 and this will be off. This will be 1, this will be off, and this will be on, this will be on. So whatever A data that you are getting will be going to Y. So when S is 0, Y is A. Similarly, when you give S, Y will be B. So in this way, we are realizing the MUX. So how many transistors are needed here? So this needs 1 transistor, this need 1, this need 1, this need 1. So 1, 2, 3, 4, and this will need 2. So we are needing 6 transistors. But if you see this MUX and this MUX, it has the same select line. So we need S and S bar, right? So we can give the same S to both the MUX and same S bar to both the MUX. So we don't need 2 inverters. We can give 1 inverter, and this S bar also we can give. This S bar also we can give to this MUX. So for this MUX we need 6, and for this MUX we need 4. And again here there is another MUX which has a select line A 0, 1, and for this we need 6. So 6 plus 4, 10, and 6. So we need 16 MUX. So for the each MUX we need 6. For the bottom MUX we need 4, and for this MUX we need 6. So if you see, if we are going to the lookup table based way, then the number of transistors that we need is actually increasing, right? Hello.
Sir, your voice is not audible and I didn't get the working of MUX, sir. Could you please repeat, please?
Yes. So consider S equals to 0. Say S is equals to 0. Here the value will be 0, right? And NMOS will be off when S is 0. And again, we have an inverter here. So the value here will be 1. So when the value is 1, this is PMOS. PMOS will not work when the voltage is high. PMOS will work when the voltage is low. So both these transistors will not work, and S equal to 1. So this NMOS will work. This work as a short. And when this S is 0, here we are getting 0. and this will be short. So A will be going to Y. So Y is nothing but A when S is 0. And Y will be equals to B when S is equals to 1, which is nothing but the implementation of this mux.
Okay.
So for this mux, we need 6 transistors. But here we are using inverter to get S bar. For this mux also, we need B and B bar. So we will use one inverter and B bar will give to both the implementation. So for the bottom mux, we don't need the inverter. So we need only 4 transistors. And there is
Sir,
another
that
mux.
point I am not getting, sir.
See. Here you need 1 transistor, right? Sorry. See, here you need 1 transistor, right? And here you
Yes,
need
sir.
another transistor. Here you need another transistor. Here you need another transistor. Here you need
Yes.
2 transistors.
Yes, sir.
But for this implementation, you need S and S bar, right? For S bar, you need a NOT gate, right? For this, you are using 2 transistors. I am saying this mux and this mux both need B and B bar, right? You don't have to generate B bar for this mux separately and for this mux separately. You can use the B bar that is being generated for this mux to this mux. Understood?
Okay.
I'm saying you don't need 2
Okay.
inverters. I'm saying the same signal you can use for this mux. So this won't need the inverter, and that's why here we'll need only 4, and here you will be needing another 6.
You are saying that the select line for these 2 muxes
same.
is same, right?
So we don't need separate implementation. We can share the same signal for both the mux.
Yes, sir. Sir, do we need to understand the CMOS implementation of all?
No. This is just to distinguish between the ASIC versus FPGA. This is you don't have to completely go in detail. You just have to understand that in the case of LUT-based implementation, the cost will be high. That is the actual point that I'm trying to make. So I hope
Okay.
till this point you have understood. So what I'm
Yes,
trying
sir,
to
it's
say is,
clear now.
yes. So this is ASIC-based implementation, and here we need less number of transistors, whereas here we are needing more number of transistors. If you can see, right?
Yes, sir.
So what I'm trying to say is here the cost will be very less. This is hardware optimized and also very efficient because the power consumption is less. The number of transistors that are needed to implement this is less. So it will have very less loss and it will be highly efficient. But in order to make say whatever chips that you will be seeing with the pins, if you want to reach till this stage, you have to make the layout and you have to send for fabrication, and it will have very long development time, and the design is fixed. See, once you have made the IC, you cannot change the design, right? It will be only for this NAND gate, but you cannot change it. Whereas in the case of LUT implementation, even though the cost is high, it will increase the overall cost of the implementation. Also, the power is high. The power will be very high. One advantage is you can always configure, like this is FPGA-based implementation, right? You are writing the code in Verilog, you are dumping in the FPGA. If you write a different code, you can still again dump in the FPGA. Whatever code you want, you can still dump in the FPGA and the FPGA will modify accordingly. So here we'll have this configurable option in the case of FPGA. So whatever way you want the hardware to be working in, according to that, you will write the code and you will just simply dump in it, which is very easy for us for the hardware testing. So because of that, we are going for the FPGA implementation. That's why we have selected FPGA for this course. So whatever Verilog codes that we'll be writing in the future, we'll be dumping in the FPGA and testing the hardware. But when you have fixed the when you want it to be made into product, then you will go into the ASIC implementation. Until and unless you want the product, you will not go to ASIC implementation. We'll use FPGA for any research purpose or teaching purpose. People might use some microcontroller, which I will also be discussing in the future. And FPGA is we will rigorously do in the FPGA, and whatever Verilog coding that you will be needed will again be taught by sir, and I will also be showing you many examples and clear your doubts. So you don't have to worry about learning Verilog, that will take care. So for this reason, we are going for FPGA. Even though the cost is high, I agree the cost is high, but we need the flexibility. We want the code to be dumped and immediately FPGA has to work according to our code, which cannot be done in ASIC. It has to be sent for fabrication and the IC has to come, which will be taking a lot of time. And again, we cannot change the hardware. If you want another code, again, you have to send for another IC, which we don't want. So that's why we are going for FPGA. I'll be briefly discussing about FPGA. And again, this is just to understand how FPGA works. You don't have to memorize all these things. This is just for your basic understanding. So FPGA full form is Field Programmable Gate Array. So it is a semiconductor device that is based on the matrix of it is based around matrix of configurable logic blocks connected via programmable interconnects. So these are the logic blocks, and these are connected by this programmable FPGA. Sorry, programmable interconnect. So this programmable interconnect connects this logic block to the input-output block. So it has mainly three modules. One is the logic blocks, where whatever code that we are dumping, that will be converted into this configurable logic block, and this programmable interconnect connect this logic block to the input-output pin. All these things will be mentioning in the code. So which input-output pin we'll be using, and whatever code that we'll be writing, that again will be discussed in the future. So this will interconnect will directly connect this configurable logic block to the input-output block, and it also has special blocks called block RAM and DSP slice. So if we want to discuss something about configurable logic block, which is also called as the CLB. CLB mainly consists of a lookup table, which we have already discussed. So it consists of mainly this logic function that we'll write in the Verilog code, and it will also consist of multiplexer for selection of logic, which will be going to this output, and it will again go to the input-output. And it will also have D flip-flop to store the output of the lookup table. You don't have to bother much about it. You just have to understand what details are there in the FPGA. And for FPGA, people use different kind of hardware description language. One is Verilog, another is VHDL, System Verilog. These two are quite popular and they are used much. And in this course, we'll be discussing about Verilog only. And we'll be teaching you the Verilog code, how to write Verilog code, how to implement our digital control logics in Verilog. And the VHDL is not needed for this course, only we are using Verilog. So, and these are some differences between FPGA and ASIC. It is not that FPGA.
Sir, what does ASIC mean, sir? ASIC expansion, please.
Of what?
ASIC.
ASIC is application specific integrated circuit.
Okay, sir. Okay, thank you.
So it is very application specific. Application specific IC means integrated circuit. So it is specific to that particular application. So you might have seen there will be gates, NOT gate, AND gate, NAND gate, IC. So they are very specific for that application, NOT gate, NAND gate. In the case of FPGA, you can write code for NOT gate, NOR gate. You can dump it again. So you can change. You can. It is not fixed. You can reconfigure it at any time. Depending upon the code that you are dumping, it will change accordingly. So there are trade-offs between FPGA and ASIC. So FPGA has some advantages, some disadvantages. ASIC has some advantages, some disadvantages. Considering our requirement, we are using FPGA because it is easy to dump the code again and again and implement multiple control algorithms in the FPGA. So as far as this course is concerned, we'll be using FPGA throughout the course. But again, if you want to make into a product, then you go for ASIC implementation because it is very compact in size. It comes in a very small size. Like the IC, it has again different packages depending upon the packages. So it will be very power efficient, but the making of ASIC will take a long time. Whereas in the case of FPGA, it will be very simple. You just have to write the code and dump in the FPGA. So this is the FPGA that we'll be using in this course, which is the Xilinx Mimas Spartan 6 FPGA kit. So these are the input-output pins. So whatever ADC data that is getting converted into digital, and whatever digital data that will be again going into DAC, we'll be using these pins to send the data. Not only digital analog, also if you want the switching frequency or if you want the PWM signal, all these signals will be going to that signal conditioning board, using this input output ports. And it has some other push buttons also. So there are, so here I think 40 pins are available, and here 40 pins are available. If you want the details, I have mentioned the link here. So when I share this PDF, you can go through and you can refer to this. And this is the power supply, and it also has push buttons, LEDs, which you can reconfigure. You just have to mention everything in the code and dump it in the code. So this is the IC that we are using. So like this is a basic picture of the IC. So coming to the control techniques, I think as far until this point is concerned, I think everyone is clear. If you have any doubts, you can stop at any time. Hello. Hello.
Sir, how much this will cost? Is it possible for us to get this?
I do not know the cost of this. You can like when this PDF is shared, you can go to this link. It is their official website where they'll be mentioning about the cost, pricing, everything, within how many days they'll be delivering. So also you can search directly in the Google Xilinx Mimas Spartan 6 FPGA, and you can see. I am not currently aware of the cost, and I don't know what is the current cost of this FPGA.
Is this the hardware we'll be using for our implementation? Sir?
Yes,
In
yes.
this
Whatever
course?
we are going to implement in this course, the code will be dumped into this FPGA. So this has been used, and whatever hardware results that SAR is showing, that is using this FPGA.
Yeah, okay.
Okay. So before, so this is all about FPGA and ASIC. So I hope I was able to make you understand about the importance of digital control and why are we going for FPGA, not ASIC. So till this point, I hope I'm clear. If you have any doubts, you can ask me. So now we'll be moving on to the control techniques. So there are so many feedback and feed forward control techniques, which will be used depending upon the requirement. And you should be thorough with these control techniques, because we'll be implementing these control techniques, digital control techniques in the FPGA by means of Verilog code. So you have to be very thorough with this control technique. So this is a buck converter. So we are sensing this output voltage. See here, we are sensing the, this is a current sense amplifier. So we are sensing this current, and regarding how we are sensing, all this will be discussed in week 5, I guess. So you don't have to bother about the working of this current sense amplifier. That will be discussed in the upcoming weeks. So we are sensing V0 and we are sensing IL. This will be going into the FPGA where signal processing. So whether they will be going into ADC, all those things that will happen here. And again, we'll be using different feedback or feed forward control methods. That is again up to us, which control technique we are going to use. So all this thing will be written in Verilog code and dumped in the FPGA, and we'll use different modulation techniques, and we'll give the gate bus, which will be going into the gate driver for both the switches. So we are currently concerned about this feed forward and feedback control. And then after this feed forward feedback control methods, we'll be going into the modulation techniques, different modulation techniques that are available, and which we are going to use in this course. So sorry. So these are the different feedback and feed forward control methods are available. Voltage mode control with and without input voltage feed forward. Current mode control with and without current load current feed forward, and DC droop, as well as state feedback control. The control can be either linear or non-linear, and fixed frequency control or variable frequency control. Again, we'll be discussing this in the upcoming slides in detail. And multi-mode control. If you want to know about these controls in detail, SAR has already made another course, Control and Tuning Methods in Switch Mode Power Converters. The videos are available in YouTube. You can go through those control methods in detail. Now, you can call voltage mode control as single loop control. Why? Because it has single loop, right? So here, this is V0. And there is only, this is a sensor. Say we are sensing the V0. Say V0, we are passing through some resistor divider, R2, R1, V0, and whatever hardware we have made, we have implemented in the same way. We have used the resistor divider. So what this voltage will be R2 by R1 plus R2 into V naught. So this R2 by R1 plus R2, we are calling it KC. And heads up, within 10 minutes again, this session will be closed. I'll join in the same link again. You please, whenever this meeting is ended, please join in the other meeting. So this is KC, sorry, KF. So this is the feedback gain, which is going to feedback, and V reference minus V naught is the V error, which is going to the controller GC, which will give us the control voltage, and is then compared with the ramp. Now this will go to the PWM block, which is this SR latch, and it will generate the Q, which is the gate pulse, and it will go to the gate driver, and the switches are turned on accordingly. So I guess someone was asking me if there is any noise, how are we going to eliminate it using RS latch? So let me draw here. This is the ramp, VR ramp, and control voltage. Let me use another color. Let me use blue color. So here they have given some noise, right? So here there is noise, and here also there is noise. So if you actually give the comparator output will be noise, because if this VCon is more than VRAMP, then output will be 0. If VCon is less than VRAMP, then output will be 1. So whatever reset signal, like whatever signal QC we will be receiving, that will have this noise. Yes, you are right. But whatever Q we are having, it will be pure. Why? Because see, this is an SR latch, right? So whatever switching frequency we are considering, so this is the switching frequency pulse that we are considering. So fixed frequency, again, this is a fixed frequency control technique. So whenever this FSW rising edge will be seen, S will be 1. And at the what is the reset pulse? So this is the set pulse. And here we are having this reset pulse. So V ramp, right? So V ramp is lesser than VCon. So it will be 0. And say here we have some jitter ramp, the reset. I'm really sorry. So here we have this jitter. Because of noise, we are getting this signal. Similarly, here also we are getting because of this noise, right? So this is the scenario. This is the set pulse. This is the reset pulse. So let me change the color again. So whenever this set is 1, so at this point, the set is 1 and reset is 0. So what will be the output? 1. QE will be 1. So during this region, so let me draw the Q pulse here. So during this region, it will be 1. And in this region, both set 0 and reset is 0, right? When both set and reset is 0, it will retain the previous value. So whatever value that it is having here, it will, it will retain the same value, isn't it? So it is having a value of 1. So 1 value will be retained here. And when you receive a reset of 1, so here we are receiving a reset of 1 and set is 0. So set is 0, reset is 1 means it will get reset. So when it got reset, now reset is changing to 0, right? So in between we have reset value 0, but set is 0, reset is 0, it will retain the previous value. So it will still retain the previous value, which is 0 because it got reset here. And again, reset has become 1. It will still be reset, and reset has become 0. It will retain the previous value 0. So even if there is noise, because it got reset once, and even if R is becoming 0, both are 0 anyway, and it will retain the previous value. So it will retain the 0 value until you get the set pulse 1. So again, it got set here, and again, it will get reset here. So whatever noise that we are getting in the reset, it will be not reflected in Q because of this SR latch. The SR latch will work in that way, right? If both S and R are 0, whatever is the previous value, it will be retained. So because of this SR latch, we'll get a clean signal here. So even if there is noise in the VCon during this comparison, it will not be reflected in this side. And one disadvantage of this voltage mode control is we are taking only V0, but there is no control over current, right? We are not bothered about current. So we are not regulating current. We are only bothered about V naught, but we do not know about current. If you want to limit the current, say the current cannot cross 10 amperes in the circuit, it might damage some components. We cannot put any saturation limit here. We can only put the duty ratio limit, but we cannot put any current limit during load step up transient. If you want to put any limit on the current, we cannot do that because it is a single loop control. We don't have control on current. But how can we do that? We can go to the two loop control, which is yes.
Sir, could you please repeat that noise once?
Okay. So I am saying, say this is the set pulse, which is coming from FSW, which is a fixed frequency. So this set pulse is FSW. Reset pulse is coming from the comparison. So I'm saying if there is a noise, reset will toggle multiple times, 0 to 1, 0 to 1, 0 to 1. And
Sir,
again,
here, like, sir, when the V ramp is greater than V control,
then it is become,
only-
then only it will become 1. So the output is VR greater than VCon. Then QC is 1. So at this instant, VR is crossing VCon. So this is VCon, right? The blue is VCon, the red is VRAMP. So until this point, VRAMP is less than VCon. So the output is 0. So reset, this QC pulse is the reset pulse, is 0, right? And during this condition, if VCon is having noise, so it might cross VR multiple times and might come back like it might be greater than VR multiple times and less than VR multiple times. So there will be multiple switchings at the reset pulse.
Yes,
Right.
sir. But at the end, like when the noise in the V control is completely removed, then the V ramp is greater than 1. Sir, then the R will not be low,
Sorry.
sir.
Sorry. This will be 1, completely 1. Sorry, I'm wrong. So there will be jitter and it will be completely remaining 1. Yeah, you are right. Again, here
Yes.
reset is 1, set is 0. So the value will be 0.
Sir, please, sir, could you please elaborate here? That like for yes, it is 1. That's fine. When the reset R is 0, then the output will be set 1. Okay. Then 0, 0 memory state, it will be 1.
See, when set is 1, reset is 0. So output will be set to 1. And now set has
Okay.
become 0 and reset has become 0. So it will retain the previous value, which is 1. Until there is a reset that has come. Now reset is 1, set is 0. So now it got reset and it got 0. Now even if reset is, see, assume that reset has become 0. Set is already 0. So it will retain the previous value, which is 0. So it will stay here. And then when finally reset becomes 1, it is reset 1, set 0. So it will be 0 only completely.
Okay.
And at this moment, VR is coming less than VCon. So reset will become 0 and we have seen a set value as 1. So it will again set here. So whatever noise that multiple switching is coming here, it will not be reflected in the output because of this SR latch.
Okay, sir. Okay.
So in this case, there is no control over current. If you want current to be also controlled, we have to go for current mode control. So here we have two loops. Outer loop is this V naught loop.
Sir, why we are moving for two loop control, sir?
So in this case, we don't have control over current, right? We are only bothered about V naught. But if you want, say current, there has to be some limit, right? Current cannot go very high.
Why, sir? Why the current is going high here?
See, I'm saying, say if there is a load transient, I naught, and the inductor current waveform is like this. Say it is going like this. This peak, if you want to restrict it, you cannot do anything here, right? This is not in your control. But if you want to control this peak, you can do that in current mode control by keeping a saturation limit on this. Here we are not bothered about current. So that's why there is no control over current in the voltage mode control. Actually, there is less than a minute. So this meeting will be stopped at any moment. If this meeting is stopped, please join the meeting in the same link again. No, there is not a possibility of both set and reset becoming 1 because we are only making set 1 at this instant and throughout the time it will be 0. So there will not be any instant where set and reset will become 1. So the only possibilities are 1, 0, 0, 0, 0, 1. 1, 1 is not possible. So if you want to limit this maximum current, it cannot be done. So we have to go for current mode control where we have control over both current and V naught. That's why we are going for current mode control. I hope I am clear. Hello. Hello, am I audible?
Yes, sir, you are audible, sir.
Okay, let me share my screen again. So whatever I'm trying to say is in the case of voltage mode control, we are taking the information of voltage. So whatever we are going to make, it will be reflected in the voltage, and we don't have any control over current. If you want to control current, you have to sense it, and you have to do some operation on the current. Else, how can you control the current? So for that case, we are going for current mode control, where it has two loops. Mainly the outer loop is V0 and the inner loop is IL. So the outer voltage loop will give this feedback voltage, and this feedback voltage will be going to this V reference minus V feedback operation, and this will give us V error. This will go to the controller, which will give us this reference value, which is being like compared with this IL reference, and this will go to the reset. Whereas in the case of voltage mode control, this inner loop is not there. Now we have connected this inner loop. Actually, we can put a saturation here. If you want to put a saturation, you can saturate it. You can saturate it. So even if the value is more than that, we can put a saturation limit. So it will not cross that voltage. So we can put a saturation limit on current. So if you don't want the current to cross say 10 amperes, you can put a saturation limit and it will not cross 10 amperes. Whereas in the case of voltage mode control, you do not have control over current, and that is one advantage of current mode control. And the inner loop has to be 10 times faster. Whenever we have multiple loops, always the inner loop has to be faster than outer loop by 10 times.
Can't we interchange like outer current and inner voltage?
No. Current loop
Why,
has
sir?
to be faster. So
Why,
like current dynamics has to be faster than output voltage dynamics. Voltage is
Sir,
always the outer
like-
loop. Yes.
Sir, based on the voltage will be the current, right?
Yes, but current has this ripple information, which the voltage does not have. So current will be the inner loop and voltage will be the outer loop. Someone is running. And this inner loop has to be faster than the outer loop. And this is not in this case. If you go in any other application, whatever maybe the inner loop has to be faster than outer loop, and the thumb rule is 10 times. And because of this,
Sir, I didn't understand why only the current loop has to be in inner loop. The reason
the professor says that the chance of ripple of the inductor current developed from the load current is 20 to 30% of the nominal value.
yes,
But in the case of voltage ripple, it is only 1 to 2%. That's
Yes.
the reason why we are giving the inner loop as current.
yes,
The voltage loop as to outer loop.
and this current has this ripple information which output voltage lag.
Sir, please repeat that the point.
So like whatever IL that we'll be considering, this has a ripple information of 20 to 30% ripple, whereas this V0, which will have only 2 to 3%. So the dynamics of current is faster than V0, and because of that, the inner loop is inductor current and outer loop is the voltage. And this is thumb rule is 10 times faster. Not in this case, any case. And because of that, the dynamics of current mode control will be reduced order dynamics, and it will also simplify the controller design. So because of these benefits, we might go to current mode control. I hope I'm clear.
Sir, what does it mean by 10 times faster? Where we have to be faster? Which variable?
So like in the sense, say this VCon is changing, right? Whatever change this VCon is, like say there is a delta VCon change. This delta VCon change should be reflected in Q, right? And this inner loop is responsible for changing this Q for a given change in VCon, right?
Okay. Yes.
So whatever change in the VCon has to be reflected in Q. So if this inner loop is slower, before it gets, see, VCon is changing like this. If the inner loop is slower, before it gets like change the value of Q before it responds to this change in VCon. VCon is again changing. So inner loop should respond much faster than the outer loop. So whatever change in the VCon will be immediately reflected in Q. And whenever there is another change in VCon, it will be reflected in Q. Say if inner loop is slower, whatever change that is coming in VCon, it will take some time to respond in Q. And before the Q will get changed, again VCon will get changed. So whatever change that is coming from the outer loop will not be reflected in Q. So that's why always the inner loop should be much faster. So inner loop will respond quickly to whatever change that is coming from the outer loop. I hope I am clear.
The inner loop must change 10 times faster than the
Like the bandwidth, if you see the border plot bandwidth, it has to be, yes, 10 times faster. Yes. Okay, I hope I am clear. So now coming to fixed frequency and variable frequency control techniques. In fixed frequency, there are multiple techniques called pulse width modulation, pulse shift modulation, and pulse skipping modulation. In the variable frequency, so in this pulse width modulation, here all the frequencies fixed. In this case, duty ratio is variable. We are only changing the duty ratio. Fixed frequency is same. In pulse shift modulation, there will be two pulses, and sorry. So there will be two pulses, and the phase shift between these two is being varied. In this course, we are not considering this phase shift modulation. It will be used in other AC/DC converters, so no need to bother about. In pulse skipping modulation, we are skipping the pulses. This will be actually operated in light load condition. So regarding this, we can discuss in detail when it comes in week 10 or week 9. So currently, you can remember that in pulse skipping modulation, sorry, there is something called charge cycle and skip cycle. So it actually skips pulses. So it will be on for some time in one cycle, and in the next cycle it will be completely off, and in the other cycle it will be on. So let's not bother about this. We'll discuss in the upcoming weeks. So sir will be discussing this in detail. In constant on time, like in variable frequency, frequency is variable. Here in this constant on time is fixed. In this constant off time is fixed. In hysteresis, both are variable. Both on time and off time are variable. So we'll be discussing this control techniques in the upcoming slides, where we'll be discussing about the architecture and everything. So
one small question in this constant
yes.
on-time modulation.
Yes.
I have seen few data sheet where it is mentioned that the frequency range can be set by us.
Yes. So like we are fixing
if the frequency is variable, then what is the purpose of we setting the frequency externally for that constant on-time ICs?
What happens is see, whatever this frequency is there, FSW, it will like if the frequency is very large, then the ripple will increase, right? The delta IL is inversely proportional to switching frequency in majority of the cases. So if the frequency is going very low, then delta IL will keep on increasing, which will increase the loss. So again, there is a trade-off. So they put a lower limit on FSW, which will put an upper limit on delta IL, so that it will not go below that, and it will not increase the ripple. The ripple will not be very huge. If FSW becomes very lower and lower, then delta IL becomes very higher. So they put a lower limit on FSW.
Even it has an higher limit on the FSW.
And
what's the purpose?
Cannot like there will be you cannot operate it at higher frequency, right? It again boils down to the architecture and the hardware that you are concerned. So there will be still some limitation. So again, the frequency is coming for the input and output voltage that you are selecting. So based on say V input has some range and V output has some range. So considering the worst case scenarios, there will be switching frequency varying, right? So what will be the maximum switching frequency and what will be the least possible switching frequency, which is again coming from here. So depending for the given set of V input and V output, there will be a maximum switching frequency, and from there you are getting. And again, switching frequency cannot be very high, because if you increase the switching frequency, switching losses will increase. So usually they'll keep the limit within which the switching frequency will be operated.
So though we set the frequency in the design, still the frequency is variable. So that is
Yes.
only for us to
Yes,
have
yes,
an arbitrary value, right?
Yes, yes, yes. Actually, this frequency range is wide. It is not very small. So let me go back to the slide where I have shown this commercial IC. So here, if you can see, it has it is, I think, a variable frequency, and frequency is operating from 200 kilohertz to 5 megahertz, which is not actually a small margin. It is a quite margin, and considering the ripple and everything, they have set this margin. So it will not go below 200 kilohertz, and it will not go above 5 megahertz. So that is the limit they have considered while designing. So it is not actually very narrow. So within this region, the frequency will be variable, and I think depending upon the load requirements and the input output voltage requirements, they have designed this. So the frequency is variable, but again, there has to be an upper limit and lower limit, right? Frequency cannot go 0 and infinity. Depending on the, as we are doing it practically, the ripple losses, everything will come into place. If the switching frequency goes very higher, the switching frequency losses will dominate. So, and if the switching frequency is very less, the conduction losses will dominate. So they consider this trade-off, and they'll put this limit on switching frequency, both upper limit as well as lower.
One small question. What is the reason behind the efficiency improving as we decrease the switching frequency?
Efficiency improvement. So there is this trade-off. So if you consider switching frequency, if switching frequency is high, then switching losses will dominate. Switching losses will dominate, and this will be more, and conduction losses will reduce, because switching frequency is high, so the ripple will be less, RMS will be less, so comparatively conduction loss will be less. Now if you reduce the switching frequency for the same L and C, you have designed L and C, and now you are varying switching frequency. So now if you are going to low switching frequency, the ripple will increase, and since switching frequency is less, switching losses will reduce, and conduction loss will increase. So this trade-off is there. Depending upon that, so for a fixed frequency, if you consider a plot, so we are operating in a, say, the fixed frequency, and we are operating efficiency versus I naught. For a buck converter, the efficiency curve will look something like this. So as you go on to the higher I naught, as we have seen, so switching frequency is fixed, and I naught we are increasing. So current will increase, that is passing through inductor, and conduction losses will become dominant. So the efficiency will be less. And when you are operating at light load condition, and if you are operating still in fixed frequency, the switching losses will dominate, and the efficiency will be good.
Okay.
So that's why for light load conditions, they use light load. They will not use pulse width modulation. They use something called pulse skipping modulation that we'll be discussing in the upcoming slides. So for light load, there are multiple modulation techniques which will increase the efficiency at light load. And again, they are only for light load. When you're again moving for high load, then we'll be moving to other techniques. If it is fixed frequency, we'll go for pulse width modulation and variable frequency. So each of them will have trade-off. I think Sar has explained by means of a table what is the RMS worst case scenario in fixed frequency, in constant on time, constant off time. So each one will have different advantages. It's not that one will have all the advantages, other will have disadvantages. There will always be trade-off. You should choose depending upon your requirements. So if you want one, you have to sacrifice other, somewhat sacrifice other. So it cannot, like, one fixed frequency cannot be better in all scenarios. So what they usually do is, so they operate in in one modulation technique at one certain load conditions. One certain load condition, and at the higher load they'll operate in other modulation techniques. So we are changing from, say, pulse skipping modulation to pulse width modulation. So this is called multi-mode because you are operating in multi-mode. Again, it is not so simple because you should decide from where, at what point of I naught you are shifting from PSM to PWM, and the transition has to be smooth. All these things will come into picture. This Sir has discussed in the like I guess week 11 or week 10, where Sir has shown the hardware results when it is moving from PSM to PWM. So this will do for higher efficiency. So at lighter load, we are not losing any efficiency, and for high load, reasonably high load, we are shifting to PWM. So this is called multi-mode architecture, and Sir will discuss about this briefly in the week 10 or week 11.
Okay, during some cases, even if we design if we select the inductor having say like 20% peak to peak,
Okay.
but in maximum means while designing or choosing this L, we will be considering the peak, maximum load current. Okay?
Worst case, yes.
But,
for everything,
yes,
you'll consider the worst case.
but what I have seen is that even if I have designed it for that case, the peak-to-peak ripple current is actually going like 200 or 300 times the load current, but still the output ripple voltage is like only 30 or 40 millivolt maximum.
Yes, yes.
But
See,
what is the reason behind this?
So there are two things. One is IL, delta IL. Another one is delta VC. So IL thumb rule is 20 to 30% ripple of the average inductor current. So say delta IL is equals to, you are considering 20%, say 20% of the I naught, say average. So maybe I will say IL. So you are designing, this is designing the L. So the thumb rule is inductor can like operated in a way such that the ripple is around 0.2 times IL. Whereas coming to the output side, delta VC or delta V naught is around 2 to 3% of V naught. So delta V is say 0.03 worst case of V naught. So we are designing the capacitor in such a way that the output ripple is not so much. So the voltage is like stable, like the output voltage, we want it to be stable, right? We don't want much ripple, and thumb rule is 2 to 3%. So you design a capacitor in such a way that the output ripple is 2 to 3% of the value. Say if you are operating at 1 volt, then 2 to 3% is how much? 3 by 100. So around 30 millivolt. So 30 millivolt is the ripple that you will observe at the output for 1 volt. Say you are designing 30 millivolt. I hope I am correct, right? This is 30 millivolt. Yes. And say the current is 10 amperes and you have designed it to be 30%. So 3 amperes is the ripple. So you are designing in such a way that this is 20 to 30%. So whatever you are considering for the designing of
Actually,
LNC,
what is happening is I'm getting peak to peak ripple as 200% and not 20%. But
then
still, the output voltage is maintained the constant. And even if we connect say load, the load current is actually a flat line. But the inductor switching current is actually reaching 200% or 300% of it.
Okay. Are you operating at light load? Actually,
no.
See, I am telling for a buck converter, whatever L you have chosen, whatever input. Okay, maybe let me discuss one thing. Say for V in minus, V in minus V naught is equal to L into delta IL by DTS, right? So this is the equation that decides the inductor current ripple. So delta IL is nothing but V in minus V naught into duty ratio DTS by L. So now you are not getting any I naught dependent term here, right? So whatever may be your I naught, it will almost remain same. There will be some effect. It's not that there won't be any effect. So whatever value of L that you are designing, you should consider 20 to 30% of ripple. But you are saying 200 to 300% of ripple. You should not like always compare. This is 20 to 30% is of the worst case scenario. So this is for I naught max. Now you are operating at say I naught max is 10 amperes. You have designed the inductor in such a way that the ripple is 3 amperes. Now if I am operating at 1 ampere, still the ripple will be 3 amperes because delta L is not independent of I naught. But you should not say that this is 300%. You have designed the inductor for the worst case scenario, which is the maximum current. For that maximum current, the ripple is 3 amperes. Now, if you reduce the load, the ripple will still be the same. That is the issue when you are going for again light load if the ripple is high. That's
Okay,
why,
got it.
and again, we are operating in continuous conduction mode. Because of this, the ripple is less. So people go to DCM mode to reduce the like ripple. So inductor current will not cross zero. It will limit the ripple. That's
DCM
where.
mode is like a pulse skip modulation, right?
Yeah,
Or,
pulse skip modulation also comes under DCM, and like there are multiple modulation techniques that come under DCM. And DCM is the like overall family, discontinuous conduction mode, where inductor current cannot go zero, and pulse skipping modulation is one such technique.
okay.
So this is why. So when you are operating in light load, the ripple will still remain the same. We have designed it for the worst case scenario. So when you are operating at the maximum load for a buck converter again, this is not applicable for other converters. For buck converter, worst case ripple happen at maximum load current, at which you generate like you decide the value of inductance considering 20 to 30% of the ripple. So this is about fixed frequency, variable frequency. Now there are leading edge and trailing edge PWM, which we call. Again, trailing edge have voltage mode control, current mode control, average mode control. And leading edge will have voltage mode control and current mode control. And constant off time is analogous to trailing edge PWM. So that's why I have put them in the left hand side and this on the right hand side. And the constant off time will have voltage mode control, peak current mode control. So constant off time control is analogous to peak current mode control. Only here switching frequency is same, here off time is same. In constant on time we have voltage mode control and valley current mode control. In this current mode control, the fixed frequency is fixed and duty ratio is varying. Here on time is fixed and off time is varying, but both are analogous to each other. Coming to voltage mode control, I think yes.
What is valley current? And actually, when we are comparing voltage, we can actually generate a constant voltage source.
Yes.
But how the current comparison is actually carried out here?
Okay.
Valley
yes.
current and
peak current, right?
no, valley current and how the current is actually compared.
Okay. I'll
because when voltage comparator we can have a fixed reference that is easy to generate.
Yes.
But how it is carried out
for
in
the current mode control? Yes, I'll be discussing. So first I'll be discussing about the voltage mode, then I will go to the current mode. It is in the 2 slides away from this. So as we have discussed.
Hello.
Yes.
Actually, previously you are designing about that ripple based on inductor, right? I have one doubt. If this is for butt converter, okay. Suppose if you place an inductor in the AC, if you have an AC source, AC to DC, if you are placing an inductor, then the delay is that delay also same.
It is like this is for DC converters. I'm not exactly sure about AC to DC converters. I have not worked on it, so I'm not exactly sure how inductor is designed.
No, it's atom pole PFC is there, right?
Yes.
Have you heard of? Yeah, so there will be source and inductor. So here the inductor will take the average value of it. But
yes,
in
yes.
AC
In
side,
DC converter,
value
again, this is for DC converter. AC to DC converter, it will again vary. The techniques for designing the inductor, I am not aware of because I am working on DC converters. I am not working on AC to DC converter. Actually, there is another session tomorrow by another TA, Calvin Joseph. He is actually working on totem pole PFC.
90 to 65.
Hello.
Tomorrow, okay.
Yes,
fine.
tomorrow 6 to 8. Another TA, one of my friend, he is taking the session. Actually, he is working on totem pole PFC, so you can ask him. He can elaborate more. And I am not working on that, so I won't elaborate.
Yeah, fine.
Yes.
Thanks.
So, okay. So this is I'll discuss about the current mode control when peak current mode control is coming, how valley current mode control is coming. So in voltage mode control, we have the V reference, and from feedback we are getting feedback.
65.
Sorry, I think someone is unmuted. Please mute yourself. So this GC is the controller. This is the V error. This output of GC is giving the control voltage, which we are comparing with the RAM. And I have discussed, even if there is noise here, it won't be reflected in the Q. So the switching frequency is the set pulse, and QC is the reset pulse. And using this SRLH, we are getting this Q. So in the voltage mode control, it is a single loop control. We have only output voltage loop, and we are designing the controller, which is giving VCon, which is being compared with the RAM. Now coming to the trailing edge, coming to the trailing edge current mode control, which is also peak current mode control. So here, what do we have? I'm writing the plus minus. V reference here, V feedback here. We are giving the controller, and this is giving us, say, I reference or icon, whatever here they have written. Now this is being compared with IL. Previously in voltage mode control, this is not IL, this is RAM. Now instead of the RAM, we are comparing it with the inductor current. And previously it was compared with RAM, which was generating reset pulse. Now we are comparing it with inductor current, which is giving us the reset pulse. And since it is fixed frequency, here we have FSW and Q. Say this is icon and this is the inductor current. Let us draw the reset pulse. So whenever IL touches icon, there will be a pulse of reset. So actually,
Sir, sir, excuse me, sir, is there any like the feedback is always subtracted from the reference?
Yes, because we have to get the error, right?
Yes, sir. But here I control is the reference, right?
Yes. Actually, you are getting confused. It is a two loop control. So this is one loop, the voltage loop, and this is the current loop. So for outer voltage loop, V reference, the output voltage is the reference, and V naught is the feedback. For the inner loop, we are getting this icon from the outer loop, and this acts as reference for the inner loop.
Okay.
And if you and someone is asking how do we design GC, that will
Yes,
be
for inner loop, what is the reference?
Icon that is coming from the outer loop. So this act as a reference. So you can consider this as a reference. So whenever this is touching this point.
Yes, sir. You are saying that reference is subtracted.
Like here you are subtracting. Here we are using the comparator. It is similar to like a reference. Here we are using a comparator. Here you are using a controller. Here it acts as a reference signal, and here we are using a comparator to generate the reset signal.
Yes, sir. Does it here the symbols are exchanged?
Which symbols?
Like, are we subtracting feedback from the reference or not in the current?
No, not subtraction. We are just comparing it to get the reset pulse. Similar to this, analogous to this one, where here you are generating the ramp signal. Here you are getting the inductor current. Here ramp is always fixed. The ramp is always fixed from 0 to VM, and it is always fixed. And only
Yes,
V1
sir,
is coming from
but-
the outer loop. Whereas here the inductor current
Sir, the
is
thing-
coming from the loop.
The thing I'm confusing is
Yes.
whether the feedback is subtracted or compared by this.
Yeah, it is being compared because this is the inductor current, right? So that's why you are like compared. Whereas in the case of
No,
average mode-
actually, hello.
Yes.
Actually, he's asking IL should be minus. Like IL.
No. This is a
coming,
comparator.
taking the-
Like we are not generating the error. The error you will generate when you are using the average current mode control. Here it is having ripple, so that's why you are comparing it. Whereas in the case of average current mode control, you will filter out the ripple, and IL you will get I average, and in that case you will subtract it. But here, as the peak information is written, you will directly compare it. You will not subtract it. Same with the valley current mode control. In the case of average current mode control, then only you will generate the error, and then another control element will be there.
Yeah, okay, fine.
So now whenever this touches, we'll get a reset pulse. So this is the
Sir,
reset
I'm
pulse.
not clear with what I have asked, sir.
Okay, you are saying why we are comparing it, why we are not subtracting it, right?
Sir, for giving reset pulse, whether always the reference is having plus and the feedback is minus or not, please clear me that thing.
Yes, so
first.
this will vary depending upon whether you are using a peak current or valley current. So for peak current, now let me change the color. So for peak current mode control, set pulse is coming from FSW. and reset pulse will be coming from loop. This is for peak current mode control. For valley current mode control, which I will be discussing in the next slide, it will be different. Reset pulse will be FSW and set pulse will be coming from loop. And here inductor current is hitting, the peak of the inductor current is hitting I reference. So the waveform is like this, where this is for the peak current mode control, because we are controlling the peak. Peak is coming from the loop. Whereas in the case of valley current mode control, it will be like this. So this is the valley, right? This is the valley current mode control. And both are like analogous to each other. Only here minus becomes plus in this case and set becomes reset in this case. So if I go to this valley current mode control, if you see here icon is having minus, IL is having plus. Here icon will have plus, IL will have minus. And this is giving the reset pulse. Here it is giving the set pulse. And FSW is set in the case of peak. Here it is set of like he's giving the reset pulse. So that is the difference.
Why
Yes.
the difference, sir? What happens if the ulta is taken?
See, like you have to come from the waveforms every time. So here we are resetting it, right? So when you are resetting it, the inductor current is going down. And whenever it hits this minimum valley current, it has to turn on, right? So whenever this hits this icon, it should generate the set pulse. So in order to generate the set pulse, so whenever IL is crossing icon, it should generate the set pulse. So IL should be minus, icon should be plus. So whenever it touches, IL is just less than IL and it will generate the set pulse. So it comes from the logic. Whereas here, it will generate the reset pulse, right? So reset pulse is coming from the loop. And when is reset 1? When IL is greater than icon. So whenever it hits, we'll get reset. So this gives the sign, plus sign here and minus sign here. Understood?
Yes, sir. Like in single voltage control loop, how that is different, sir?
So here in current mode control, you are comparing the reference with the inductor current. In the case of voltage mode control, you are comparing the reference with the ramp signal. That's how voltage mode control is designed. And this is how current mode control is designed. Here VRAMP is always same. Always same. But here it is coming from the loop. IL is also varying dynamically with the loop.
Yes, sir. But in previous case, like in voltage control, like if I take ulta for the comparison, then is there any problem with that?
See, again, you have to consider this one. See, the set pulse is coming from FSW, right? So the reset pulse is coming from the control loop. So when the reset pulse becomes 1, from here, you can say when the reset is coming, the reset is coming at this junction. So at this point, VR is greater than VComp, right? So VR should be positive and VComp is negative. So whatever control technique you are using, you can first draw the waveforms. From the waveforms, you will know the signs, minus or plus. This cannot be plus and minus, because if that is there, then reset will become 0 at this point. So how you want it to work, that decides this minus and plus. And this is for trailing edge. When you go to leading edge, it will be exactly opposite. This will be plus, this will be minus, this will be set, this will be reset.
Okay, sir. Okay.
Everything will be just opposite to each other. So this is the peak current mode control. And for valley current mode control, it will be exactly opposite. And here, whenever inductor current hits peak, reset will come. Here, whenever inductor current hits the valley, set will come. Just the opposite. So you don't have to remember both. If you can understand this one, you can do the exactly opposite thing and you will get the PWM generation block of valley current. I hope I'm clear until this point. Hello. Hello.
Yes, sir, you are audible.
Okay. So I'll continue. Whereas in the case of constant off time is fixed. See, this off time is fixed. and on time it is coming from the loop. And I have told you here, off time is analogous to peak current mode control. So whenever the inductor current hits the icon, which is coming from the loop, it will reset. And until what time it will reset, that is constant, the T off that we are deciding. So after this constant T off is done, you are again setting it. Sorry, you are again setting it, and whenever it hits the peak, again it will be off for constant time. So this on time is coming from the loop. This is coming from the loop, and this is fixed. Same thing. So in the peak current mode control, icon is minus, IL is plus. Here also icon is minus, IL is plus. You are getting it right? And someone is asking me why minimum off time in constant on time. Actually, that at this point I'm not saying because it will be very hectic for you. It is discussed in week 2 and 3. At that point, I'll explain you elaborately why that minimum off time should be there. Actually, it is related to the loop. If it does not happen, the loop will collapse. So that we'll be discussing during that time. So if I tell you that now, it will be too much for you to digest. So let's discuss about the modulation techniques. In that week, I think in the next week or next to next week, I'll discuss that. I'll remember that and then discuss. So constant off time is analogous to peak current mode control, and constant on time is analogous to valley current mode control. And in the case of current mode control, you will be comparing the currents. In the case of voltage mode control, you will be comparing the voltages, and rest parts remaining same. So this is T off, and the on time will be coming from the loop. Here also off time is fixed, on time is coming from the loop. And now if you go to constant on time current mode control, which is again, yes, there is a tuning methods course prerequisite for this course, which is control and tuning methods, which is also done by Dr. Santanu Kapat, and you can refer to that. So there, Sir will show you MATLAB simulation case studies, and he will explain in detail the control aspects, how this is working. Maybe I can share you the link by the end of this session. You just remind me.
Sir, is it mandatory to watch that course completely?
No. So whenever Sir is discussing this course, in between, Sir is mentioning at the bottom that this has been discussed in lecture 12. This has been discussed in lecture 13. So if you want further details and information of that lecture, you can go to that particular lectures. You don't have to go through. But if you go through, that will be a benefit, but you don't have to go through. Wherever it is necessary, Sir will mention which lectures are useful, and you can watch those lectures. So in constant on time is again analogous to valley current mode control. That's why, sorry, I think this is constant on time voltage mode control, not current mode control. And that's why we are comparing the voltages, and on time is fixed, and again off time is coming from the loop. So on time is fixed, and whenever it will turn on again, that is coming from the loop. And this is current hysteresis control. In the case of constant on time, I'll again go back here. So in the constant on time, T on is fixed. In constant off time, T off is fixed. In hysteresis control, both T on and T off are variable. Then what is fixed? The ripple. We are considering the ripple of the inductor current. So we are setting the upper limit, which is Imax, and we are setting the lower limit, which is Imin. Again, the session will be closed in 1 minute. After the meeting is done, you again please join in the same link, and we'll continue the discussion. Say the average current is I0. Imax is nothing but I0 plus delta IL by 2, and Imin is I0 minus delta IL by 2. So whenever it hits the valley, it will turn on, and whenever it hits the peak, it will turn off. And the same thing is realized using two comparators and set reset flip-flop. Till this point, is this clear, or shall I repeat the current hysteresis? Hello. Hello. Hello.
Sir, it's audible.
Yes. Okay. So let us join. I think only 2 participants have come. Let us wait for some time. Yes. So let us continue. So in current hysteresis control, we are fixing this ripple around this I naught, around this average current. We are fixing the ripple I naught plus delta IL by 2, I naught minus delta IL by 2. So whenever this current is hitting this peak, we are turning it off. And whenever this current is hitting this bottom, we are turning it off. So this ripple is being fixed, and you can decide this delta IH. So you can either increase or decrease depending upon your requirement. And here it is not like it varies, right? On time, off time, we are not controlling that. We are only controlling the ripple. So this ripple constraint is giving the on time as well as off time. So this is all about the current modulation techniques and everything. Coming to digitization in switch mode power converters. So there are 2 things, right? Single loop control as well as 2 loop control. Consider the single loop control, which is the voltage mode control. So in single loop control, we want to digitize. So from this point to this point, it will be digitized. Let me check someone else coming. So IMAX and IMIN are generated by outer loop in hysteresis. No, actually this we are designing. I naught is decided by the load current, and delta IL by 2 is up to us. So delta IL, you can fix it. You have to fix it. Delta IL. So this IMAX and IMIN, that is being fixed by us. Whatever the inductor current ripple has to be, that you are deciding, and the IL is accordingly following. Say I naught is 10 amperes, and you want the ripple to be 3 amperes. So IMAX I will keep 11.5 amperes, and IMIN I will keep 8.5 amperes. So it is up to me. Whatever the value it has to be, I am choosing, and the inductor current will follow accordingly. So delta IL by 2 is again our wish, and we are designing it, and I naught is decided by the load current. It is not in our hands. So this is all about modulation techniques. I know this will be a bit heavy for you. You have to go through the lectures again and again to grasp this knowledge in a good way. So I recommend you to, again, this entire session will be available in YouTube. You can go through this, or you can go through SAR's old course. But I suggest you to go through the lectures if you are facing any difficulty, because when we move on to the next week, week 2 and week 3, SAR will not be again discussing this in detail. We assume that you have understood, and we'll go to the further concepts. So if you are not clear, I suggest you to go through either this recording or SAR's recording, so that all the concepts will be clear. And but I believe you are still having doubts. So I suggest you to go through SAR lectures. And if you are still having doubts, we can again discuss in the next week session. So coming to the digitization, as I have discussed, so this entire loop we are making digitized. So again, V0 is in analog, right? This is in analog. So we are digitizing it. So we are using analog to digital converter to make it in digital. And someone was asking, V reference, are we generating from the auxiliary supply? No, this is being generated in the FPGA itself. This is also a digital signal, and these are being subtracted in the code. So after this, from this, everything will be in Verilog code, which we'll be discussing in the upcoming week. So this V error voltage, this is also digital. And now this compensator is digital PID, not analog PID, digital PID. But how will you be implementing digital PID in Verilog? That will be coming in the Verilog. Whenever SAR discusses about Verilog, it will be discussed. Sir, please share the lecture is uploaded. Okay. Okay. NPTEL does not share the link. Achha, I see. Okay. I'll share my YouTube link, my YouTube channel link at the end of this session. And also I will share the SAR's previous year control and tuning method course link so that you can go through it. Sir, if you can please mention the sessions which we have to more important in exam point of view from my past experience. Okay, I'll share the link of my YouTube channel and also the link. So like I'll be discussing the problems. Since this is week 1, there are many concepts that Sar has discussed, and there are not many problems that I can discuss. So as you can see, it is very conceptual and all the concepts has to be clear. From week 2, we can discuss more problems. So from week 2, so from next Monday, it will be of more problems, and less part of will be conceptual. As week 1 is more introductory, you have to understand all the modulation techniques which has been covered in the last course. That's why I have spent more time on making you understand the control techniques and modulation techniques and how we are digitizing this. So all these concepts are covered in the week 1. So that's why, is it needed to attend tomorrow's session 2? It is not mandatory, but it is up to you. And someone had doubt regarding the inductor design in totem pole PFC. I suggest that person to attend tomorrow's session. If you have any doubts, you can attend in tomorrow's session. It's up to you. If you can attend any one of the session or you can attend both the sessions. Anyway, we'll be both discussing about week 1 that Sar has covered. So you can attend my session or his session, and or you can attend both the sessions. So it is up to you. If you want him to explain something else, I can inform him. Yes, he will also be explaining similar concepts and few problems. So accordingly, only for week 1, it will be more conceptual. From week 2, it will be more problem solving, because week 1 is highly conceptual and it is really mandatory for you to understand clearly so that you can understand the rest of the week's problem. So this is digital PID, the implementation of digital PID in Verilog. All those things will be coming in the next weeks. And again, this is a ramp. In the case of analog, you are generating a ramp, right? Like this, it is a smooth function. Whereas in the case of digital controller, this is not a ramp anymore. It is coming from the counter. So in digital, it has discrete values, say 0, 1, 2, up to so on, final value and 0. So here we have infinite resolution. It is smooth. Whereas here, it is not smooth. It is having some minimum step size, which is counter. This minimum step size will be coming in the case of digital ramp, which is not available in analog. Analog, it is smooth function. Whereas in the case of digital, it is this ramp. So if you see Vcon is here. So Vcon is here means the duty ratio will be like this. And if Vcon is here, the duty ratio will be like this. So there is this minimum duty ratio step. So if you see this delta D TS, so you cannot get the duty ratio in between this because it is having this step size. It is not possible for us to achieve a duty ratio between this step. So duty ratio will be also in stepwise. Say this is D1TS, this is D2S, D2S, and then this is D3TS. So this delta D difference will be there because of digitization, and this will cause some stability issues, which we'll be discussing in the upcoming weeks. So keep in mind this digital counter will have discrete jumps, which will be reflected in the duty ratio like discrete. So now say, see, this is the counter, right? So if say the delta TSW, this is switching time, and each step, the horizontal step is having T clock. The clock frequency will decide this each step. So now how many steps are there? Number of steps is nothing but TSW by T clock. If you want it to be finer resolution, so if you want to reduce this delta D, you have to reduce this T clock time. So if you reduce this T clock time, number of jumps will increase, and delta D, this delta D will decrease. Again, I cannot make this T clock infinite, right? So whatever T clock that we are using in this course is 100 megahertz. So whatever 100 megahertz is, how much? 10 nanoseconds. So this jumps will be of 10 nanoseconds. Again, that will be reflected in duty ratio. So duty ratio is not continuous. Duty ratio is discrete. But if the clock frequency is high, the discrete jumps will be very small. So it depends upon the clock frequency that you're choosing. If I am going to 500 megahertz, then it will be 2 nanoseconds. And the delta will be 1/5 times of what we are getting from this. So this is one very mandatory thing that we should be taking care about. It is unlike analog where it is smooth. Here duty ratio is smooth. It can vary from 0 to 1, but here it jumps in discrete manner. So we may not get 0.44444. So we have to adjust to the nearest, say 0.45. Nearest, you will take the nearest 0.45 depending upon the jumps and the clock frequency. Higher the clock frequency, finer the resolution of the duty ratio. And now this is being compared. Again, this is a digital comparator. Again, this is a digital comparator. And this is digital flip-flop, which will be writing in the Verilog. This will be writing in the Verilog. And the output will be going to the gate driver. The output will be going to gate driver circuit. And it will generate the pulse. Someone has a question. When will you upload this video? So I will be trying to upload by this Wednesday. So I need some time to upload it. So I'll try to upload it by this Wednesday. I will share you the YouTube link, my YouTube channel link today. So in the case of two loop control, there are two loops, right? So which loop to be digitized? So here there are two scenarios. One scenario is the architecture one, which we call mixed signal. Why we are calling mixed signal? Because it is analog plus digital. So it is having both analog and digital. So outer loop, we are putting in digital. So V0 is in digital and current is in analog. So as I told, inner loop should be faster. That's why we are keeping this in analog and the outer loop in digital. So outer loop will be digital and this reference will be in again digital, right? This is coming from the FPGA, but this signal is analog. You cannot compare digital to analog. So again, you need DAC to make it into analog. Now these two analog signals are being compared with each other, which will give us the reset pulse and FSW also set pulse. Now this is going to the DC-DC converter. Now you ask me why we are keeping analog inner. As I told, inner loop should be faster. That's why we are keeping in analog, and the outer loop will be in digital, and inner loop will be 10 times faster. Now, what you may ask me, what happens if I put this also in digital? So coming to that, so what level of control analogies are required for this course? So you should have basic understanding about all the modulation techniques that I have discussed in this session. So if you have any doubts, I suggest you to go through this recording again, or I suggest you to go through SAR's previous course. You can find that. I'll share you the link at the end of the session.
Sir, no. This I'm asking about the control system.
Control system,
digital,
not
much.
You should have, if you have done UG control systems course, that should be enough. So like you should know about say this control, how we are writing the control. You should know about the transfer functions, and you should know about Bode plots. You should know about small signal transfer functions, and you should know about controller design using a pole zero cancellation approach. These all are taught in UG control course. So all this knowledge, basic knowledge should be enough. Even if you are facing some difficulty, I think SAR has elaboratedly explained in this course, so you can while going to the course you will understand. But if you are facing any difficulty, say if you are facing difficulty in Bode plots, you can refer to any books only for Bode plots. You don't have to go through the entire control system course. So wherever you are facing some difficulty, you can go to other control systems NPTEL course or any reference books that they provide. You can go to that books and you can understand this Bode plot. But I guess these are like very basic, and these are taught in UG control. But even though if you are facing difficulty, no issue, you can refer to any control system standard books, or you can visit other control systems NPTEL video lectures and you can refer. So this is what, yes, sorry.
I have another question.
Yes.
In the introductory video of this course,
yes.
Sir was talking about that high voltage, low current application.
Yes.
Actually, where, which part of the circuit does he actually referring to? I don't know,
Okay.
because
Actually, it
high
is
voltage-
very specific to one. What shall I say? Very specific to one application called multi-phase buck converter. So I am which I am currently working on. So the example I have given here. So this controller IC that I have discussed about, right? So this is actually a multi-phase buck converter. So this is a buck converter. So it has gate driver and switch inside. This is the switch node. This is the inductor. This is capacitor. So this is buck 1. And this is buck 2. This is buck 3. So similarly, they are saying we can consider 10 such buck converters. So multiple buck converters are connected in parallel. So that's why we are calling this multi-phase buck converter. Now, so many questions might be arising in your mind. Why we are connecting them in parallel? Why so many converters are connected in parallel? And how do I know how many converters I should connect in parallel? Actually, it is very specific to multi-phase domain. But I don't know, other people might or might not understand. So if you have any queries, we can discuss about this later. But currently keep in mind, all these inductors are connected in parallel. Say this average current is IL1. This current is IL2. This current is IL3 up to so on IL10. You just remember that output current is the summation of average inductor currents. So it is sigma ILI. I is equals to 1 to 10. So what they usually do is when say the current is very high at the output, they connect multiple buck converters in parallel so that the current is divided. Say the current is 50 amperes. I am using 4 phase, say 4 buck converters I have connected in parallel. Each converter will take how much? 12.5 amperes.
12.
So there is actually a reason why we are connecting this in parallel, but I'm currently not going into that because it will be too much for you to understand. But maybe we can discuss later. We can have a good talking session.
So this is a high current application.
Yes, high current application.
High current and low
voltage.
low
And
voltage.
again, voltage will be very low. So this has different applications. So as you are saying, low voltage, high current applications. It has data center application. It has automobile application. And it has a smartphone application. So in your smartphone also, you will find this multi-phase converter, and in automobile also you will find this multi-phase converter, and in data center VRM application also multi-phase converter is widely used.
So from where, after which value we can say that is a high current? Is there
That
anything
also,
specific for
it
this?
actually there is a lot of conceptual knowledge that you will be needing for this. So maybe I would suggest we can have a session later, because so many questions will arise. Now you can ask me, what if I use 2 converters instead of 3? What if I use 4 converters instead of 3? There is like a technical reason behind that. So maybe we can discuss in the later session. You just remind me, maybe I can discuss in the later session. But it will take some time. I need around 20-30 minutes to discuss completely regarding this multi-phase.
Sir, I'm asking, is there any value above which we will say that is a high current? Is there any specific value?
Yes, it actually comes from the efficiency curve. So that's
Okay.
what I can say.
Okay.
And someone is asking, sir,
Thank
does this code helps to understand the digital control of DC to AC converters too? No, we are only discussing about DC-DC converters, and the hardware results that Sarah has shown is limited to buck. But whatever control aspects that we are discussing, it can be applicable to DC to AC. There might be some difference in this what can I say, modulation technique, but overall concept remains same. See, we are only discussing about digital control and how it is being implemented. For your application, maybe this architecture will change, but the implementation, the Verilog coding, everything will remain same. So we are designing this and implementing this for a buck converter, which is a very basic converter. So it is a basic converter to start with, so that you can also understand easily, and control and designing everything will be simpler compared to other converters. So this is just to make you understand how we are digitizing everything. What is the necessity of digital control? How we can use FPGA and how we can write very long code. But if you are using for different say AC to DC converter, there the modulation technique, this entire thing will change. But you have to write the code accordingly. We are not teaching how we write code for that. We are making you understand. We are making you learn how to write the code. So for your applications also, you can use the same knowledge and apply them. It will be difficult, of course, because buck converter is a simple converter to start with, and we are teaching for this, so you can understand the concept, but you can extend it to your converters. So in the case of two loop control, as I'm discussing, there are two architectures. In one architecture, outer loop is digital, inner loop is analog. In the other architecture, inner loop is also digital. Now there are so many challenges in this case because inductor current is there, right? It has ripple information. So you have to sample it so many times to retain this ripple information. So this ADC clock frequency, this ADC frequency should be very high in order to get the ripple information. If it is low, then you will lose the ripple information. But if ADC is high, sampling frequency, power loss will be high and efficiency will be less. Or one thing they can do is they will sample at a point and they will emulate the inductor current inside the FPGA. The details of this will be discussed in the next week. Sir will be teaching digital current mode control. Sir will be teaching about two things. One is the fully digital current mode control. This is fully digital current mode control. And another one is mixed signal current mode control. You don't have to bother about this. This will be taught by Sir in the week 2 or week 3. This is mixed signal. You just have to understand in mixed signal, current loop is in analog, voltage loop is in digital. Whereas in fully digital, we are saying fully because both current loop and voltage loop are in digital. This will have many stability issues compared to this mixed signal because this is in analog, this is in digital. This will come with a lot of challenges. But why we are doing this, it also has some advantages because current loop is in digital. We have the flexibility to do whatever we want in the code. That flexibility will be there. And if we can actually take multiple digital control techniques, we can actually, if you sense the inductor current, we will have so many advantages because now we have inductor current. We can write like different high level algorithms in the very low. We can use this inductor current in our control. So we can say use this inductor current and we can like use it like a feed forward in this digital. So for different control modulation techniques, it will be used. And many IC commercial ICs that are coming now, some of them are sensing the inductor currents. So some the IC that I have discussed, let me go back to that session. So here, this CS current sensing, so it is going back here. So some of the ICs, they sense inductor current and then they emulate it inside and they'll write the control technique or whatever modulation technique they're going to use. So it is also one such advantage that we'll be getting, and Sir will be discussing this in the upcoming. So monitor. Sir, please share your email ID, please. Please let us know the difference between feedback and feed forward. So feedback means like it is feeding back. So if we are considering a plant, I'll write it here, plus minus, say GC controller, GP plant, and this is V0. Now this is feedback. So it is feeding back. It is feeding back to the reference. But say if I have a summer block here and I'm adding this, now this is feed forward. So we are adding it. You are adding it. So this is called feed forward. And this is called feed. This is called, sorry, this is called feedback. So this is every control we will have feedback. Sometimes we use feed forward for better advantage. Currently, I'll not be discussing in detail. There is something called input voltage feed forward. It will actually improve the transient performance. And there is something called load current, I load current feed forward. Why we will be using this, how it will impact the loop, that again sir will be discussing. At this point I'm not telling you because you might face some difficulty in understanding this. So you just keep this in mind. There is something called input voltage feed forward that we'll be using in the upcoming weeks, and also the load current feed forward to improve the transient performance. Okay, feedback minus, and you cannot say that feedback minus feed forward plus, because this will come from see, this is minus means this is negative feedback. If this is plus, it is positive feedback. Something like that. So again, feed forward can also be plus, can also be minus, depending upon your requirement, whether you want to add it or you want to subtract it. That depends upon your application. And usually feedback will be negative because negative feedback is stable, positive feedback is unstable. But also there are some applications where we use positive feedback, like Schmidt trigger, where you use positive feedback. But majority of the applications we use negative feedback, it is stable, and positive feedback is unstable. Yes, positive feedback makes unstable, but you may ask, then are we not using it anywhere? Yes, we are using one such example is Schmidt trigger, where you use positive feedback. So this is all about the control and modulation techniques. And I suggest you to go through SAR's video lecture as well. Coming to power stage design, I am not spending much time here because we are already running out of time. And I'll discuss very few aspects. So Sir has already discussed this in the class. So this is the delta IL of buck converter. Using this, say this 20 to 30% of inductor current. Based on that, you will design L. So current ripple you use to design the inductance L, and delta V naught you use to design the output capacitor CO. So these derivations are explained in the previous course, control and tuning methods. You please go through those lectures. If you are facing any difficulty, please let me know in the next session. I will derive everything, all these expressions, how we are getting this, how we are getting this. And IL RMS square is I naught plus delta IL square by 2. How we are getting this, Sir has explained in the course, previous course. Again, Sir has, so this is the formula for deriving IRMS. So using this formula, you try to derive this expression for this. So this is x1, this is x2, and this is x3. So average is IL, x2 is IL plus delta IL by 2, x1 is IL minus delta IL by 2. And this time is DTS, this time is 1 minus DTS. So using this formula where Sir has mentioned this, you try to derive it. I was planning to derive it in today's class, as but we are running out of time. So you try to derive this. If you are facing any issues, I will be discussing in the next week. And I will also be checking if you have derived it or not. So that will give you this IL RMS square. And why we are using this IL RMS square? For say calculating power loss. You will need this IL RMS. So for that purpose, we are calculating this. Similarly, in boost converter, you can get this delta IL, delta V naught. This will be used to generate like design inductance, and this will be used to generate the output capacitance. And this again, the worst case scenario, all these things, I hope you will be understanding this. But if you face any difficulty, please feel free to ask me in the next session. I'll be discussing very elaborately. And this is the IRMS for piecewise linear waveform. This is the formula that you can remember. And this is actually very good formula, so that you can calculate the IRMS easily. It's very easy. Please try to use this to prove this. And if you face any difficulty, we'll discuss in the next session. So there are some options. Sir, does it not feed forward makes it unstable? No, it will not make. In fact, it will improve the system performance. How it will improve, that again, Sir will be discussing in the next session, like in the upcoming weeks. So as promised, I'll be sharing you the link of Sir's previous course. Yes.
Sir, that digital loop is slower than analog loop is because of the limitation in clock frequency. Is it sir? The digital control loop,
yes,
is slower than the analog loop is because of the limitation in clock frequency.
Not actually slower. We can still be able to reach the same bandwidth, but one issue will be there. it has a stability criteria because of that digitization, everything. It will post some stability criteria because if you see ADC, it will have some delay. And if you see the computation, everything, it will have some delay. So this delay will be added in the loop. It will create some issues, but sir will be showing how we can achieve higher bandwidth by means of different tuning. Yes.
Sir, in this Zoom, actually chat is the only way we should ask questions, right?
No. You can unmute yourself and you can stop me at any time. You can ask any questions. I will be replying to you chats also.
No, that is not what I mean, sir. Because some questions you are reading which is not showing up in our chat box.
No. Actually, some people are mentioning in the chat. Maybe they're messaging only me. I request students. You make the questions visible to everyone, so others will also see. I just know. Maybe they are mentioning only to me. That's why I'm reading from there and I'm answering to that person. I suggest the students. It is not allowing me to unmute. Ask to unmute. Maybe Banerjee. Okay. If you are facing any such technical issues, you can mention in the chat. I'll try to rectify them. Or you can also mention in the chat. I'll be checking the chats. But it would be good if you can unmute yourself so we can chat each other and I can better understand your queries and you can better understand the solution. So I have shared the YouTube link in the chat where this is the control and tuning method of SARS video lecture. Okay. Someone is asking me my email ID. I am sharing. It is tj2281@gmail.com. So I hope everyone got my email ID. Also, let me share my YouTube channel link. So currently I have not uploaded any videos, but I will be uploading. Just please let me know if you can see my YouTube channel. Is it accessible or not? Can someone please confirm? If possible, if we switch some other platform like Teams, it will be good. Kindly consider, sir. Actually, the issue is once we have generated the link, it is not possible to change the link. I am using Zoom because here I can record it automatically. Whereas in the case of Teams, I have to use my institute email ID, and I don't know whether I can upload it to YouTube because I will be using institute ID. But here I'm using my personal ID, so I can upload it to YouTube. So due to these constraints, I'm using Zoom. But only issue is the session is 40 minutes. Only thing we have to rejoin it. Except apart from that, I guess Zoom does not have any issues. Here I can auto record, so it will be recording automatically. And if you are facing,
will it be?
Yes.
Sir, in YouTube, will it be available as a single link? Because we are cutting with 40 minutes.
Yeah. I will merge all these videos and I'll add it as a week one single video. To merge those videos, I need some time. I'm also busy with my work here, research work. So I need some time. I will be trying to upload. YouTube link is not working. So I have not uploaded any video. That is my channel link.
Yeah, link is showing up, sir.
Yes. Okay. Link is showing up. Fine.
It is showing.
Okay. So I have not uploaded any video. I will merge all these videos, make it a single video. I will upload it there. Whatever SARS lectures are available, I will also mention in the description. So when I upload it to YouTube, you can go to the description, whatever lectures and everything that is mentioned there, I'll mention in the description. So you can go through, and I have mentioned my email ID. Please feel free to contact me if you have any doubts. So if your doubts are clear, we can end this session here. Okay, then I'll end the meeting and I'll upload it to YouTube, and the link will be shared by the NPTEL. If not, you can you have the access to my YouTube channel. You can directly watch the video when it is uploaded. Okay, thank you, sir. When will we do the problems? So in the week one, it is morely about conceptual things. So that's why we have not solved any problems, and there are not many problems that can be solved from week one. So from week two, we'll be solving problems. I'm planning to do in this way. First 1 hour, I'll be discussing concepts, and if you have any doubts, you can ask me. In the entire second 1 hour, we can solve problems. Okay, then see you in the next week. Bye.